For over a century, Americans blamed bad coal for the thick, black smoke pouring from their mighty steam trains, while across the Atlantic, British locomotives glided by almost spotless. Yet laboratory tests from 1904 reveal American engines sometimes had better fuel. So if coal was not the culprit, why did U.S. trains ignite such colossal clouds? The real reason is not just about engineering. It upends what you think you know about how geography, economics, and ambition shaped the very machinery of progress. And once you see the real reason, you will never look at those iconic plumes the same way again. Laboratory records from the early 1900s tell a story that turns conventional wisdom on its head. Chemists at the Smithsonian and the Pennsylvania Railroad collected samples from both sides of the Atlantic and put them through rigorous tests. The results were clear. American anthracite coal, especially from the Pennsylvania fields, contained less than 5% volatile matter. In contrast, the bituminous coal fueling most British locomotives registered between 30 and 40% volatiles, a chemical signature that should have produced far more smoke if left to burn unchecked. Yet, in practice, American engines often blanketed the countryside in thick black clouds, while British trains ran with barely a trace. The paradox deepened when looking at the numbers. Anthracite, with its low volatile content, is prized for burning cleanly. Bituminous coal, loaded with gases and tars, is notorious for producing smoke unless managed with precision. Despite this, photographs from the 1920s and the 1930s show United States giants like the Pennsylvania Railroad M1 class trailing vast plumes, while British expresses, like the Great Western Railway kings, left only faint wisps behind. Coal quality alone cannot explain the difference. American trains had access to some of the world's finest, cleanest burning fuel, yet still filled the sky with smoke. The real mystery lies elsewhere, hidden behind the numbers and waiting to be uncovered. In the early 1900s, American newspapers helped cement a simple story. Coal was to blame. The New York Tribune in 1911 declared that railroads were forced to burn bad coal. And similar headlines and editorials spread the idea that thick black smoke pouring from locomotives was simply the result of poor fuel. Editorial writers described engineers battling through mountains of inferior stuff, painting a picture of hardworking crews sabotaged by geology and greedy suppliers. Readers saw those stories next to dramatic photographs of engines shrouded in soot, and the link felt obvious. Railroad companies, under pressure from city officials and frustrated passengers, often repeated the same claims in public statements. The belief became part of daily life, reinforced by commutes and the ever-present haze above rail yards. Even technical journals echoed the refrain, rarely asking whether the smoke was inevitable or avoidable. But the true explanation was hidden. Behind the headlines, the real reasons for those dark clouds were tucked away in design blueprints, operational manuals, and the economic logic of a continent-spanning rail network. The story of bad coal was simple, comforting, and ultimately misleading. It satisfied a need for a quick answer, but it left the real mystery unsolved, waiting for someone to ask harder questions. Stretching from the Atlantic to the Pacific, American railroads spanned more than 3,000 miles, an unbroken line across plains, mountains, and deserts. By comparison, the longest possible journey in Britain, from London to Penzance, barely reached 600 miles. This difference in scale shaped every engineering decision. In the United States, the sheer length of routes meant locomotives had to run for hours, sometimes a full day, without access to water or fuel. Railroads like the Union Pacific mapped out lines where the next water stop could be 100 miles away. The Boston and Lowell Railroad recorded water use at nearly 1,000 gallons for just 26 miles. By the late 19th century, American trains routinely carried enough water to last 100 to 150 miles between stops. For British railways, geography told a different story. The entire country fit within a space smaller than Texas, and stations dotted the landscape every few dozen miles. Trains could refill water tanks frequently, allowing for smaller boilers and more efficient firing. The limits of the land itself meant British engineers never had to design for the relentless distances that defined American railroading. Instead, they optimized for precision and control, not brute endurance. The vastness of the American continent demanded a different kind of locomotive, one built for range above all else. Water supply shaped the very bones of American steam locomotives. On routes stretching across open prairie and desert, water was often scarce, and stations could be more than 100 miles apart. Railroad operating circulars from the Union Pacific and Santa Fe railroads in the early 1900s show scheduled water stops spaced at intervals of 100 to 200 miles. To survive these long stretches, American engines needed massive tenders, some holding over 10,000 gallons of water and 15 tons of coal. The Pennsylvania Railroad's M1 class, for example, routinely carried enough to run from Harrisburg to Pittsburgh without a single refill. British trains operated in a different world. Water stops dotted the countryside every 20 to 50 miles. A typical Great Western Railway Express could expect to top up water tanks at almost every major station. Their tenders rarely exceeded 4,000 gallons, and the smaller boilers matched the shorter distances. This pattern allowed British engineers to design for efficiency and precision, with tight control over combustion, smaller fireboxes, and less wasted fuel. In the United States, the economics of distance forced a trade-off. Bigger tenders demanded bigger boilers to heat all that water, and those boilers needed larger fireboxes to keep up with the power required for long hauls. The result was a system built for endurance, not finesse. Every extra mile between water stops made the engines larger, the fireboxes wider, and ultimately the smoke thicker. The logic of the landscape was written in steel and steam. The size and shape of a steam locomotive's firebox determined how coal burned, and in turn, how much smoke poured from the stack. In the United States, engineers faced a challenge: how to keep massive engines running for hundreds of miles without stopping. The answer was scale. American locomotives like the Union Pacific Big Boy and the Pennsylvania Railroad's M1 class were built with fireboxes that dwarfed their British counterparts. Great areas on these giants reached 100 to 200 square feet, sometimes 4 or 5 times larger than the 20 to 50 square feet typical of British express engines, such as the GWR King or the LNERA 4. This was not just a matter of bigger numbers on a blueprint. The American firebox was wide and shallow, often stretching 10 feet across and sitting above the driving wheels, supported by a trailing truck. The design allowed crews to shovel in huge amounts of coal during brief station stops, creating a thick, hot firebed that could sustain high speeds and heavy loads over vast distances. The priority was simple: keep water boiling and wheels turning for as long as possible between stops. But this approach came with a trade-off. The wide, shallow firebox made it difficult to control the flow of air and the mixing of fuel. Air entered mainly from below the grates, rushing up through a deep bed of burning coal. With so much fuel spread over such a large area, some of it never burned completely before being swept up the flues and out the stack. The result was visible in the sky: black smoke full of unburned carbon and volatile gases, trailing for miles behind fast freights and mountain-climbing passenger trains. British engineers took a different path. Their locomotives ran shorter routes and could stop more often, so they did not need the same brute force. Fireboxes were narrower and deeper, sometimes less than 4 feet wide, but extending well below the boiler. The smaller grate area matched the demands of the line, and the vertical space allowed for a thicker firebed and more precise control over air entering above and below the coal. This geometry encouraged more complete combustion. Volatile gases had more time and space to burn before reaching the flues, leaving little behind but a faint haze of steam. Horsepower figures tell the story. American freight locomotives routinely delivered 4,000 to 7,000 horsepower, necessary for hauling enormous loads across mountain ranges. British express engines, built for speed rather than sheer power, often topped out at 2,000 horsepower. To achieve these numbers, American locomotives needed to burn more coal more quickly in a firebox designed for throughput rather than finesse. The engineering decisions behind these fireboxes, how wide, how deep, how much air, set the stage for the smoke that became an icon of American railroading: power. Long before sunrise, the American fireman swung up into the cab, shovel in hand, facing a day that would test both muscle and nerve. His pay, about $2.50 per day in the 1910s, was nearly double what his British counterpart earned. But the job demanded more than just stamina. On a freight run across Nebraska or the Alleghenies, there was no room for error. The fireman was responsible for feeding a firebox the size of a small room, often alone, while keeping an eye on water levels, steam pressure, and the engineer's signals. Every hill climb or sudden throttle change required instant adjustment. Miss a beat, and the pressure dropped. The train stalled, or, just as likely, a thick cloud of black smoke erupted from the stack, visible for miles. American railroads paid more, but they expected more. Higher wages meant smaller crews. On the Pennsylvania Railroad M1 class, a single fireman was expected to keep up with coal consumption that could top 10 tons on a single run. There was little time for the careful, measured firing that British manuals described. Instead, the American firemen worked in bursts, shoveling coal as fast as possible during brief station stops, then scrambling to adjust the draft and dampers while the train thundered down the line. The rhythm was relentless, especially when the engineer called for more power, opened the throttle too quickly, and the sudden rush of steam reduced draft through the firebox. The fireman, desperate to keep up, would throw on extra coal, hoping to maintain pressure. The result was almost always the same: incomplete combustion and a rolling wave of black smoke trailing behind. British practice, by contrast, revolved around specialization. Lower wages allowed railways to staff trains with dedicated firemen whose sole focus was the fire. Their training emphasized precision, thin, even layers of coal, careful timing, and constant adjustment of secondary air. The best could coax a near-invisible exhaust from even the dirtiest coal, winning prizes at company contests for smokeless runs. In the United States, the sheer scale of operations and the pressure to keep trains moving left little room for such finesse. Firemen's diaries from the Union Pacific and oral histories from the Steamtown National Historic Site recall shoveling up to 50 tons of coal in a single shift, all while monitoring water, managing injector valves, and watching for signals. During a hard climb, the fireman might be shoveling continuously, sweat running down his back, knowing that each scoop was both keeping the train moving and adding to the black cloud above. The economics of labor shaped the very look of American steam. Fewer hands meant more multitasking, and more multitasking meant less time for careful firing. The result was visible in every photograph of a mountain freight or a fast mail train: smoke pouring from the stack, not as a sign of poor craftsmanship, but as a consequence of the demands placed on the crew. In the end, the American fireman became an emblem of the country's railroading spirit: resourceful, relentless, and always racing the clock, even as the sky darkened with the evidence of his labor. In 1868, a single clause from Parliament ordered British locomotives to consume their own smoke as far as practicable. This legal demand shaped decades of railway policy and practice. Fines and public hearings followed engines that sent black smoke drifting over city rooftops. By the early 1900s, British railway manuals spelled out precise firing routines, and inspectors sometimes armed with smoke meters arrived unannounced. Liverpool's records from the 1930s show railways staging controlled tests to prove compliance, turning smoke into a matter of law and reputation. In the United States, priorities shifted. Out on the prairies, the real danger was not smoke, but fire. One stray ember could set thousands of acres ablaze. Railroads answered with the diamond stack spark arrestor, a bulbous smokestack packed with baffles to trap sparks. The design worked, but it also slowed exhaust, letting soot and fine ash collect and pour out in thick clouds. Fire prevention took precedence over clean air, and the diamond stack became a fixture of American engines from the 1870s on. Coal supply added another layer. British Railways signed contracts for Welsh steam coal with less than 2% sulfur, keeping emissions predictable. American lines bought whatever was nearby: anthracite, bituminous, even wood, leading to sudden shifts in smoke and quality. The rules, the hardware, and the fuel all shaped what poured from the stack, and how much the public learned to accept. In 1906, the Pennsylvania Railroad staged a publicity run of its new Mikado locomotive. A press photographer captured the engine charging across the countryside, trailing a smoke column so dense it was described as industrial thunder. The resulting image appeared in company brochures and newspapers, not as an embarrassment, but as a proud symbol of American strength. Smoke was recast as proof of raw power and technological might, a visible sign that the railroad conquered distance and terrain. For the Pennsylvania Railroad and its rivals, these plumes became part of their public identity, celebrated in posters and postcards. Across the Atlantic, British Railways took a different approach. The Great Western Railway's 1930s advertising campaign showcased sleek engines gliding through green landscapes, their exhaust barely visible. One poster carried the tagline, "Clean Travel" on the Great Western Railway, inviting travelers to associate low smoke with comfort, modernity, and engineering excellence. Company magazines ran stories about firemen who achieved smokeless runs, and annual contests awarded medals for the cleanest exhaust. In Britain, the absence of smoke was a selling point, a way to reassure city dwellers and impress passengers with the precision of the railway's operation. These contrasting images shaped public attitudes. In the U.S., black smoke became a badge of progress, woven into the myth of the iron horse taming the frontier. In Britain, a clean stack was a mark of professionalism and civic responsibility. Each narrative fit its environment, reflecting not just technical choices, but the values and ambitions of the societies that built the railways. Today, engineering choices still reflect the landscapes and societies that shape them. As global transit systems face new environmental pressures, the lessons of smoke and steel remain urgent. Technology always mirrors its context, not just its parts. Our priorities define what we build and what we leave behind in the air. What would your choices reveal? Share your thoughts below.